And good morning, everybody. Here are your notes and examples for section packet 4.1, and it's going to be on an introduction to antiderivatives. So an antiderivative is basically taking something that was the derivative of something and going backwards with it, so going back to its original form. So let's say we had something that we knew was the derivative of something. So let's say we had 3x squared. And let's say that we knew this was the derivative of something. So we're assuming that this is the derivative. So going back to what it was originally, we'll call that y, the original function. So what did the original function need to be in order for the derivative to be 3x squared? So we know that to take the derivative of something, you can use the power rule, so the 3 would come down, subtract 1 off the power, so we could basically reverse that process. So if you're going to multiply by the 3 and subtract 1, another way to think of that is you can go up a power and divide by that power, so to go backwards. So if you look at the value x cubed, this one you can probably kind of do pretty quickly in your head. So if we had 3x squared as the derivative, the original function had to be x cubed, because if you derive x cubed, your 3 would come down, and then you subtract 1 off the power and you get 2. So what you're basically doing is you're adding 1. So if you had your 3x squared, you're going up a power, so adding 1, and then dividing by that new power. So the new power is going to be 3, so you're dividing by 3. And then if you simplify that, your 3's cancel. And simplify your 2 plus 1, that should get you x cubed. So to reverse your power rule, you'll go up a power and divide by that power. And then there's one other thing you need to be aware of. There could have been some sort of constant at the end. So for example, if I had a constant of 7, this would also be the derivative. If you take the derivative of this, you also get 3x squared. So there could have been any kind of constant here, because the derivative of a constant is 0. So we need to account for the fact that you could have had a constant there. So what we do is we put in what we call our constant of integration, and we just call it plus c. So there could have been some sort of constant here that we don't know about that would have been 0 if you took the derivative of it. So the antiderivative of 3x squared is going to be x cubed plus some possible c value. So that is the idea of an antiderivative. And let's go ahead and look at some of the notes. Looking at your notes, we have a new symbol here. This is what we call an integration symbol, or an antiderivative. So when you see this, they're basically asking you to take the antiderivative of something, or to integrate it. It's another term for that. And what they're saying is, if you take the antiderivative of some function f of x with respect to variable x, we're going to produce something that we call the antiderivative, and they often use capital F to represent the antiderivative of something, plus some particular constant that could have been there. So plus c, that's your constant of integration. And you can always check your antiderivative by taking the derivative of your antiderivative, and it leads you right back to your original function that you are anti-deriving. So you can always double check your antiderivative by re-deriving it. So that is your antiderivative notation. This next note is just saying that if you take the derivative of an antiderivative, they're opposites, they cancel out, and you're going to be left with f of x. And this is your rule for reversing your power rule. To reverse your power rule, you multiply by the power and then subtract 1. So what's the opposite of multiplying by a power and subtracting 1? You're going to add 1 and divide by that power. So there's your rule where you're going to go up a power and divide by that power. So for example, if I had something like 7x to the 6, then to find the antiderivative of this, so remember this means antiderive, so we're going to antiderive, so we're going to go up to 7, so we're going to go up a power and divide by that power, and your 7's will cancel, and you're going to be left with x to the 7th, and then don't forget your plus c, and that is the antiderivative, and we often use the notation capital F to represent the antiderivative. So the antiderivative of that original 7x to the 6 should be x to the 7th, and you can always check this by deriving it. If you bring your 7 down, subtract 1, you get 7x to the 6, and the derivative of that constant is 0, so that all checks out. So there is your antiderivative. So reversing the power rule. And the next part of the notes is a listing of some of the other basic rules. So this one, the first one, if you are antideriving a constant, call it k, then it's going to be whatever that constant is, x, because the derivative of some constant times x, for example 3x, the derivative of 3x would just be 3, so you can think of that as reversing your power rule, or just a antideriving a constant back to the kx form, and then you have your plus c. If you have a constant that is kind of in the way, just like when we're deriving something, if your constant is kind of in the way, causing you trouble, you can bring it out to the front, antiderive the variable part, and then bring the constant back in after. The next note is, again, just reversing your power rule. So whatever your function is, call it function u. You can go up a power and divide by that power. And the last 6 are all the antiderivatives for your trig functions. You can memorize this as a new list of things to memorize, or you can just be really good at deriving your trig functions and just kind of slow down and make sure you get the one that you really want. So for example, if they want the antiderivative of cosine, the antiderivative of cosine should be sine, because we know if we take the derivative of sine, we produce cosine. And the antiderivative of sine should be negative cosine, because if you take the derivative of cosine, you get negative sine. So if you're going to get negative sine, you need that extra negative to turn it positive so that it matches up with what you had. And the antiderivative of secant squared is tangent, because the derivative of tangent is secant squared. The antiderivative of a secant tangent pattern is going to be secant, because the derivative of secant is secant tangent. The antiderivative of cosecant squared is negative cotangent, because the derivative of cotangent is negative cosecant squared. So you need 2 negatives to make that positive. And the antiderivative of cosecant cotangent is negative cosecant cotangent, because the derivative of cosecant is negative cosecant cotangent, and then you need that additional negative to make it positive like the original statement. So again, you can memorize that as a list of new rules, or you can just be good with deriving your trig functions, come up with the one that you think it is, and then just double check it and make sure that the plus and minus signs and everything work out the way they should work out. And here are some examples. So this one says solve the differential equation. So to solve the differential equation, that means bring it back to its original form. Right now the dy is by itself. So if you kind of think about where this possibly came from, it's kind of one step into the process. So if you had the derivative dy dx is equal to 3x, so what they're doing is step one, and they kind of already did it for you. You can bring your dx over to the other side. And you want to get all your variables kind of separated, left side and right side. So now all the y values are on the left and all the x values are on the right. And then you can go ahead and antiderive both sides. So the antiderivative of 1 dy should be y, because the change in y would be dy. So there's your antiderivative of 1 dy. And your antiderivative of the 3x, you want to reverse your power rule. So we're going to go, right now we have a power of 1. So we're going to go up to 2. So we're going to go up a power and divide by that power. So it's going to be 3x squared, and then divide by the new power. So that's going to be reversing your power rule, and then don't forget your plus c. And this is what we call the general solution. The general solution, because we haven't solved for c, we don't know what ordered pair this new function will need to pass through. If they give you a point for it to pass through, then you can plug in your point x comma y and solve for c. But right now we know that the antiderivative would be 3x squared over 2 plus some sort of vertical shift c for a general solution. And you can always check your answers by taking the derivative. So if you took the derivative of 3x squared over 2, your 2 would come down and your 2's would cancel. So if you brought your 2 down and you had your 3x squared, drop it down a power all over the 2 that we had here. The derivative of the c is 0 and your 2's cancel. So you're left with the original that you had, the 3x. So it looks like that checks out. So that should be our antiderivative for our general solution. And here's another one. Solve this differential. Let's rewrite our square root as a power. And they already have the dy on one side and the dx on the other side, so we can just go ahead and take the antiderivative of both sides. So the antiderivative of dy brings it back to the original function y. And for this one, we're going to go up a power and divide by that power. So we're going to have to add 1 to our power. So if we have a half plus 1, that's going to be like adding 2 over 2. So that's going to be up to 3 halves. So up to 3 halves and divide by 3 halves. And then don't forget your constant of integration, so plus c. And you'll probably see, most people would kind of clean this up. If you're dividing by 3 halves, that'd be the same thing as multiplying by the reciprocal 2/3. So that's going to be 2/3 x to the 3 halves plus c. So simplifying the dividing by a fraction piece and just multiplying by the reciprocal. And that should be our final answer. And let's look at another example. So this is just a straightforward take the antiderivative of what we have. If you have multiple terms in a row, you can just antiderive each one. And these are all powers, so we can just reverse the power rule. So the first one, the 3x to the 4th, reverse the power rule, we're going to go up to 5. So we'll go up to a new power of 5, and then divide by that new power, so divide by 5. minus the 5x squared. So we're going to reverse our power rule, and we will go up to 3 and divide by 3, plus the x. So we're going to go, right now it has a power of 1, so we're going to go up to 2 and divide by 2. And then don't forget your plus c. And there's your antiderivative, and a common notation to represent that you have an antiderivative is to call it capital F of x. So the capital F of x in calculus is often representing the antiderivative of something. And another example. So this one they want us to antiderive it, but we need to do a little bit of work first before we can actually antiderive it. So a big part of integration or antideriving is getting it ready to integrate. So if we think about what we have here, we have x plus 1 divided by a common denominator, square root of x. So you could think of this two ways. I think the way most students prefer to think of it, let's do it that way, is they think about taking this and bringing this up as a x to the negative 1/2 power. So right now it's down bottom as a x to the positive 1/2 power. And the first move that they prefer to make is to take what we have here and bring it up into the numerator as a x to the negative 1/2. So we'll say antiderivative. We'll say we have x plus 1 to the negative 1/2 power when we bring it up. And then right now we have a product, so we want to get things into more of a standard form so we can just reverse the power rule. So we want to have separate terms and not have a product to deal with. So we can distribute that through. So if we do x to the first, we have a power of 1 there, multiplied by x to the negative 1/2. If you're multiplying powers of a common base, you want to add the exponents. So that's going to leave us with a 1 plus that negative 1/2 power, so x to the positive 1/2. And then distribute into the next term. And that is going to be a x to the negative 1/2 dx. And once we have it rewritten, now we can go ahead and reverse the power rule. So the first one, x to the positive 1/2, we're going to go up a power. So we're going to add 1 to that. So we're going to go up to 3/2. So again, that would be like adding 1 or adding 2/2 with common denominators. So up to 3/2 and divide by 3/2. Plus, we're going to add 1 to the negative 1/2. So again, like adding 2/2. So we're going to go up to 1/2 and divide by 1/2. And don't forget your plus c. And again, you could rewrite that as, instead of dividing by 3/2, that would be the same thing as multiplying by the reciprocal 2/3. So it would be pretty common for the final answer on an answer key to read 2/3 x to the 3/2 plus, and dividing by 1/2 would be like multiplying by 2/1, so 2 x to the 1/2 plus c. And the next one. So this one, we want to antiderive this. This is not matching up with one of our patterns from back on our notes. So if we want to do a quick rewrite on this, so we have two factors of cosine down bottom. So we could say we have sine x over cosine x times 1 over cosine x. And we know that 1 over cosine is secant. And we know sine over cosine is tangent. And that pattern should sound familiar. What can we take the derivative of that gets us secant tangent? So the derivative of what is secant tangent? And if we know our derivatives of our 6 trig functions, we know if we take the derivative of secant, it's secant tangent. So the antiderivative of this must be secant plus c, because the derivative of secant is secant tangent, and then the derivative of that c would just be 0. So there is our antiderivative. And I believe we have one more example. So this one they want you to, again, solve the differential equation, so bring it back to the original equation. The only difference is they give you a point that they want it to pass through. So they're giving you a point, x comma y. So for this, we're going to be able to go a little bit further than just the general solution with the plus c. We're actually going to be able to plug in our point, x comma y, and solve for c. So we're going to use this to solve for that constant of integration c. So we're going to solve for c. So let's go ahead and get this started. So the x squared, I would bring that up as a x to the negative 2. And rewrite it first. And then we can antiderive. So the antiderivative of dy would be the original function y. And we're going to reverse our power rule, so we're going to go up to negative 1 and divide by the new power. So up to negative 1, divide by negative 1. And don't forget your plus c. And before you plug in your xy, you can rewrite this a little bit if you want. So y equals, we know the x to the negative 1, that can go down bottom as a x to the positive 1. We need a negative 1 so that our fraction stays negative, plus c. And right here we have what they would consider to be the general solution, but we have some more information. We know that our ordered pair x comma y is going to be 1 comma 0. So when x is 1, y is 0. So we can plug that in. So y is 0 when x is 1. So put in your x and your y, your known x and your known y, and then solve for c. So add 1 to both sides. This is going to be 0 equals negative 1 plus c. Add 1 to both sides. So it's saying that c will have to be a value of 1. And then we can go back and put that into our equation for our known c value. So y is equal to negative 1 over x, and we now know that our c has to be 1. So plus 1 for the c. And that would be your specific solution. And that should be it for the notes and examples for section packet 4.1, a introduction to integration and antiderivatives.